Does dark matter really exist? Contrary to the common belief propagated on popular science YouTube channels, modern science is far from certain about this. The hypothesis of the dark matter is widely popular within scientific circles and has numerous supporters, but it also has its fair share of critics. A recent publication in the American Astrophysical Journal reignites this debate and, in turn, questions our understanding of gravitational interactions among celestial bodies. To delve deeper, Professor Kyu-Hoon Choi, I hope I pronounced the name correctly, from the University of Sejong in South Korea, analyzed the motion of stars in so-called wide binary systems, where the component stars are separated by considerable distances, resulting in mutual gravitational forces merely a fraction of Earth's gravity at its surface. Under the influence of this weak gravity, the stars in a binary system orbit around their common center of mass. By knowing the masses of the stars, we can calculate their rotation parameters quite accurately. Here's the twist. Kyu-Hoon Choi purportedly discovered that the real rotation parameters significantly deviate from what our gravitational theories predict. It's as if the stars are attracting each other significantly stronger than what these accepted laws dictate, with deviations ranging from 10 to 30% from the expected results. However, Kyu-Hoon Choi's findings appear to align rather well with one of the alternative theories of gravity, which was initially proposed to explain other observed gravitational anomalies, the very anomalies that the most contemporary astrophysicists attribute to the dark matter. In this sense, Kyu-Hoon Choi's article strengthens the positions of skeptics, who argue that dark matter might not actually exist, and we might simply be using somewhat incorrect formulas for calculating gravitational interactions. But before we dive further into this debate, let's first discuss what dark matter is, and for that we'll have to start with gravity. Starting from the end of the 17th century and continuing until the early 20th century, Isaac Newton's law of universal gravitation was the only scientifically recognized method to quantitatively calculate the gravitational attraction between two bodies, and it served its purpose well. One of the early triumphs of Newtonian theory was the precise prediction by English astronomer Edmund Halley of a bright comet's appearance in 1758, later named after him. Even more impressively, in 19th century astronomers, armed with the formulas of Newton's law of universal gravitation, discovered Neptune and later on Pluto. These formulas also allowed to accurately calculate distances between objects in the solar system, a precision that was later confirmed through direct radar measurements. The astronomical accuracy based on Newtonian celestial mechanics even became a proverbial achievement. However, as often happens, the zenith of Newtonian gravitational theory coincided with the beginning of its crisis. In 1859, Urbain Le Verrier, one of Neptune's discoverers, identified a phenomenon known as the anomalous precision of Mercury's orbit, which could no longer be explained accurately using the law of universal gravitation. This phenomenon involves the gradual counterclockwise rotation of Mercury's elliptical orbit around the Sun. To be more precise, similar perihelion shifts are characteristic of all planets in the solar system, but Mercury's deviation turned out to be unusually significant, measuring 561 arcseconds per century instead of the predicted 527 arcseconds per century, as per Newton's law of universal gravitation. Even such a slight deviation from the previously flawless theory required an explanation. At first, astronomers hypothesized that the observed deviations could be explained by the presence of another previously unknown planet between Mercury and the Sun, which they even tentatively named Vulcan. However, despite all efforts, this planet could not be found subsequently. It took scientists more than 50 years to find the correct explanations for the precision of Mercury's orbit. The first person who succeeded in explaining this anomaly was Albert Einstein with his general relativity. This theory provided a fundamental explanation of gravity as an effect arising from the curvature of space-time near massive objects. Newton only described how gravity worked, but didn't delve into why it behaved that way. Moreover, based on this explanation, Einstein derived a more general set of gravitational equations that work even in strong gravitational fields, where Newton's formulas, as demonstrated by the Mercury's orbit, no longer held up. Shortly after the first success of general theory of relativity, a second one swiftly followed. During the solar eclipse of 1919, astronomers managed to photograph several bright stars near the solar disk, and the positions of these stars were found to be shifted from their usual positions. This was explained by the bending of light paths in the gravitational field of the Sun, a phenomenon known as gravitational lensing, and the magnitude of this lensing matched precisely with the predictions of the general theory of relativity. This was how many deviation in Mercury's orbit parameters provided a colossal leap in our understanding of gravity. It's worth noting that despite the advent of general theory of relativity, Newtonian's law of universal gravitation didn't disappear from the scientist's toolkit. On interplanetary and stellar scales, its simpler formula still worked almost perfectly, and it continues to be used to this day. Subsequently, the general theory of relativity received numerous other observational and experimental confirmations, making it one of the most rigorously tested theories in modern physics. However, just as the impeccably precise Newton's law of universal gravitation faced challenges in the mid-19th century, in the mid-20th century evidence began to accumulate, suggesting that Einstein's theory might not always perfectly fulfill its duties. One such piece of evidence emerged in late 1960s, when astronomers measured the rotation speed of stars in other galaxies around their galactic centers. According to both Newtonian and Einsteinian celestial mechanics, this speed should decrease rapidly with distance, but reality painted a completely different picture. The actual rotation speed of stars, depending on the distance, remained almost constant, as if galaxies were actually many times larger than their observable sizes. Later on, it was also discovered that galaxies weighed more than previously thought. For a long time, the only way to determine a galaxy's mass was a photometric method. We roughly know the relationship between a star's mass and its luminosity, so by estimating how brightly a galaxy shines, considering its distance, we could approximately gauge the total mass of all its stars and the galaxy itself. However, it turned out that from the gravitational perspective, galaxies interacted with each other as if their mass were approximately 6 times greater than their visible mass. Two possible explanations emerge for this phenomenon. Either our formulas for calculating gravitational interactions didn't work well on galactic and intergalactic scales, and objects actually attracted each other much more strongly than predicted by Newton or Einstein, or a significant portion of galaxies and the universe mass is composed of some invisible substance, which earned the name dark matter. The second hypothesis quickly gained dominance, and there are strong reasons for that. One crucial fact is that dark matter, which is essentially invisible during observations using our regular optic instruments, definitely exists. The term dark matter itself actually appeared long before the discovery of galactic gravitational anomalies. In 1906, physicist Henri Poincaré suggested that when we gaze at the sky through telescopes, we can only see a fraction of objects actually existing in the universe, such as stars emitting their own light and interstellar matter, reflecting, refracting, and absorbing this light. In other words, Poincaré argued that the significant portion of cosmic objects could be dark bodies that remain invisible to us. And that's precisely the case. A classic example of such dark body is our Earth. Yes, it interacts with electromagnetic radiation, reflecting sunlight, and even emitting thermal radiation in the infrared range. However, the optical effects produced by the Earth are too weak for an observer located on another star or in another galaxy to detect. For such an observer, the mass of Earth should remain concealed. There are other dim objects in the universe, such as brown dwarfs, which are failed stars that didn't quite make it to full stellar status. There are also very hot but extremely small and therefore nearly invisible white dwarfs and neutron stars. Finally, we have black holes, almost perfect cosmic invisibilities, that we can only indirectly observe through their interactions with other celestial bodies or interstellar matter. The vast majority of them remain unseen to us. So, in this sense, dark matter unquestionably exists. The question is, how massive is it compared to the mass of stars and interstellar matter? Until the mid-20th century, most scientists believed that the total mass of dark matter was insignificant. Indeed, the mass of all planets in the solar system accounts for only 0 and 14% of its total mass, and there's no reason to think that this ratio would significantly differ in other stellar systems. The same goes for the brown dwarfs. Although they seem to be quietly common in the universe, their individual masses are too small to constitute a substantial portion of galactic matter. As for neutron stars and black holes, these objects can be quite massive, but they are rare. Based on known scenarios for their formation in the late stages of massive stars' lives, it's estimated that only 2 or 3 neutron stars and black holes exist for every 1,000 stars. This rarity prevents them from becoming dominant sources of mass in our galaxy. Even accounting the mass of supermassive black hole Sagittarius A, at the center of the Milky Way doesn't change the situation significantly. However, to explain the galactic gravitational anomalies described earlier, the mass of this so-called dark matter must be at least 5 times greater than the combined mass of all stars in interstellar gas. In other words, with this hypothesis, ordinary dark objects cannot account for it. There must be something else. That something else is what people refer to as dark matter today. And when it comes to this something else, there are questions, not least because no one can say for sure what this something else actually represents. The first promising candidate for this mysterious dark matter was neutrinos, tiny uncharged elementary particles that are produced during the transformation of other particles. Each neutrino's mass is so small that we cannot actually measure it yet, but we do know that their mass is less than 10 to the power of minus 37 kilograms. Which is 1,000,000 times smaller than the mass of an electron and 1,000,000,000 times smaller than the mass of a proton. Although the mass of the individual neutrino is minuscule, there could be an enormous number of these particles in the universe, and their combined mass might indeed exceed that of regular matter. Furthermore, because neutrinos lack an electrical charge, they hardly interact with electromagnetic radiation or ordinary matter. In essence, they are nearly perfect invisibles and could genuinely be the dark matter. Unfortunately, calculations show that if neutrino were the dark matter, our universe would look significantly different from what we observe today. Astrophysicists say that our universe is homogeneous, but with an important caveat. It's homogeneous on scales of about 150 million light-years. In simpler terms, if we were to take 2 cubes of space, each with a side length of roughly 150 million light-years in 2 random locations in the universe, you would find roughly the same amount of matter inside these cubes. On the smaller scales, this homogeneity breaks down. The universe is filled with filaments or strings of galaxies with relatively high matter concentrations, separated by nearly empty spaces known as voids. These inhomogeneities, as current understanding goes, are explained by the density fluctuations in the dark matter in early universe. The smaller the mass of dark matter particles, the more homogeneous the universe should be, which makes sense. Light particles are more prone to disperse evenly throughout the space, somewhat like how fine dust particles can linger in the air for a long time, while heavier ones tend to settle. Calculations indicate that if neutrinos were the dark matter, the scale of inhomogeneity in our universe would be twice as large as we observe today, around 330 million light-years. Moreover, in such a universe, galaxies like our Milky Way would likely only just begin to form, whereas in reality we observed galaxies that are already been in existence for 1 billion of years. Far more, it should be noted that neutrinos do exist in the universe, and their combined mass could potentially be significant. However, unfortunately, they do not fit the role of hidden mass that could explain galactic gravitational anomalies. Some scientists believe that, in addition to the known neutrinos, there may exist another type of neutrino that we haven't yet detected, so-called sterile neutrinos. According to calculations, these sterile neutrinos should have roughly 10 times the mass of regular neutrinos. While these particles on the edge of being theoretical long shot could potentially serve as dark matter candidates, we have unfortunately found no signs of their existence so far, despite many attempts. Most modern researchers believe that the particles constituting dark matter must be significantly more massive, probably several times or even dozens of times more massive than a proton, and they are often collectively referred to as WIMPs, short for weakly interactive massive particles. The term weakly interacting implies that these particles would only participate in gravitational interactions, since otherwise how could they be the hidden mass, and what is known as weak nuclear interactions, which has allowed them to remain invisible for so long. The experimental detection of WIMPs is one of the most pressing challenges in contemporary physics, with dozens of research teams worldwide working on it, employing sometimes ingenious and costly experimental setups. The most promising of these experiments is the Lux Zeppelin detector, launched in 2022 in South Dakota, US. The detector consists of 1.5-meter titanium tank, filled with 7 tons of liquid xenon, surrounded by 625 sensitive photodetectors. All of this is placed within another tank made of stainless steel, filled with 238 tons of highly purified water, and installed in the bottom of a shaft 2 kilometers deep. The idea is that from time to time, WIMPs should collide with ordinary matter, in this case xenon atoms, knocking electrons out of them, accompanied by weak flashes that would be detected by photodetectors. This is at least the sixth attempt to capture WIMPs using such technology. Previous efforts ended in failure. Perhaps Lux Zeppelin will succeed where its predecessors did not, and we will finally have evidence of WIMPs' existence, providing a strong argument for the existence of hidden mass. Conversely, if Lux Zeppelin fails, it will strengthen the skeptic's position, as did all previous unsuccessful attempts to find WIMPs. Another group of scientists suggest that dark matters could be composed of known and existing particles, but in unusual combinations. One such combination is quark-gluon plasma, or more precisely a special form of this plasma known as strange matter. Quark-gluon plasma is indeed an existing state of matter, forming for instance when protons collide in particle accelerators. If protons have sufficient velocity, they disintegrate into their constituent quarks and gluons that bind this quark together. This mixture of quark and gluons is called quark-gluon plasma. However, it exists for only a fraction of a second before quark and gluon recombines into composite particles known as hadrons. This process is called hadronization. Still, under extreme conditions, such as the immense temperatures and pressures found in the cores of neutron stars, quark-gluon plasma can persist for longer periods, as long as the necessary conditions, such as temperature in the trillions of degrees, are met. Some theories suggest that quark-gluon plasma could be stable at significantly lower temperatures, if it includes a certain fraction of a third type of quark known as strange quarks. Calculations show that this variant of quark-gluon plasma, called strange matter, would have lower energy compared to regular quark-gluon plasma and even normal matter where quarks are combined into composite particles. In simpler terms, hadronization of strange matter would become impossible even at significantly lower temperature. Such matter could potentially exist not only in the cores of neutron stars, but also throughout entire stars, leading to the concept of so-called quark stars. For now, this is just a hypothesis, and verifying it is no easy task. After all, a quark star from the outside should be very similar to a regular neutron star in its all characteristics, differing only slightly in higher density and slightly lower temperature at the same rate of rotation, since the transformations from a neutron star to the quark star should involve energy absorption. Currently, there are several neutron stars that could potentially be quark stars, but debates and discussions about whether they are indeed quark stars or simply neutron stars with unusual parameters continue in the scientific community. However, even if quark stars do exist, from the perspective of dark matter it doesn't change much. As mentioned earlier, there are too few neutron stars to account for hidden mass, and quark stars are likely even rarer. Nevertheless, quark stars are not only possible form of strange matter in the universe. Theoretically, significant quantities of strange matter could have formed in the early stage of the universe evolution, when all matter in the universe consisted of quark-gluon plasma. In some regions of the early hot universe, conditions might have been suitable for creations of droplets of strange matter, which could have survived subsequent cooling and avoid the common hadronization process that result in formation of protons and neutrons. So it is possible that along with ordinary particles during the Big Bang, some clusters of strange matter, also known as strangelets, could have formed. Being perfectly stable, these clusters could have survived to the present day. These primary strangelets likely have a microscopic size on the order of an atom, but possess an enormous density exceeding that of a neutron star's core. Although strangelets must have an electric charge and thus interact with electromagnetic radiation, a matter formed of such particles would still be nearly transparent due to extreme rarity of strangelet, while still contributing significant mass, meeting the requirements imposed on dark matter. However, like other dark matter hypotheses, we have yet to observe strange matter or strangelet, even though we should have encountered them if such objects existed and were widespread in the universe. Scientists have searched for strangelets on Earth, in lunar soil, and in space environments, but all these efforts have been fruitless so far. Slightly akin to strange matter is another candidate for dark matter known as glue balls, or gluinos. In theory, they should consist of another component of quark-gluon plasma, gluons, which bind quark together with hadrons. Gluons cannot possess an electrical charge, making them entirely transparent to electromagnetic radiation, and according to many scientists, ideal candidate for dark matter. In theory, the universe could host both giant gluino stars and microscopic gluinos in size of atom or molecules, along with a variety of intermediate variations. Unfortunately, the hypothesis faces the same challenge as others. We have not observed gluinos anywhere in nature yet, Speaking of black holes, they shouldn't be completely ruled out either. Yes, black holes of stellar and supermassive masses are probably too rare to account for hidden mass. However, some models suggest the existence of microscopic black holes, including so-called Planckian black holes with a radius of 10 to the minus 35 meters, roughly a billion times smaller than a proton's radius, and a mass of the order of millionth of gram, which is about 100 billion times more massive than a proton. Microscopic black holes wouldn't participate in any interactions other than gravitational, so theoretically we couldn't detect them in any other way except their gravitational influence on other objects. This aligns with the behavior expected from dark matter, so this hypothesis is still valid, but as you've guessed, we haven't observed microscopic black holes in the natural world so far. Lastly, the most exotic candidate for the dark matter is something that isn't even matter at all, but represents topological defects in space-time. As mentioned earlier, in the theory of relativity, gravity is considered a consequence of the curvature of space-time due to a presence of material objects, or more precisely, due to their energy, including rest mass energy. Physicists like to illustrate this phenomenon by placing massive objects on a stretched elastic sheet. The heavy objects causes the depressions of the sheet, and the lighter objects scattered on it to roll toward the depression. Theoretically, the fabric of space-time can host not only gravitational wells created by massive objects, but also other peculiarities like folds, rifts, and the like, which might have formed in the early stage of the Big Bang. These topological defects, not being material objects in fact, still can contribute to the gravitational field, effectively manifesting themselves as hidden mass. By the way, we could theoretically detect such defects through the specific gravitational waves they emit, and scientists have recently devised a way to detect gravitational waves of this nature. However, we'll better save this topic for a separate video. For now, let's get to the main point. Yes, we have a multitude of theories about what dark matter might be. However, all attempts to obtain experimental evidence for any of these theories have failed miserably. Much like in the 19th century, when scientists couldn't find the planet Vulcan between the Sun and Mercury and had to modify the theory of gravity to explain the observed anomalies. So maybe the modern science is in a similar situation today. Supporters of this idea are more abundant than you might gather from watching popular science YouTube channels, whose creators adore terms like dark matter and other mysteriously sounding words, while avoiding tedious mathematical formulas. Anyway, research in this direction is actively ongoing, although with varying degrees of success. One of the most well-known ways to tweak the theory is through modified Newtonian dynamics, or MOND, proposed by Israel scientist Mordechai Milgram back in 1983. The essence of Milgram's idea is as follows. We know that in gravitational fields on the order of that created by the Earth's surface, Newton's law of universal gravitations work perfectly well. We also know that in very strong gravitational fields, the Newtonian formulas break down, giving way to the equations of general relativity, which perform admirably in those regions. But what about extremely weak gravitational fields, such as those characterizing the interactions of stars within galaxies or different galaxies with each other? Milgram suggested that in such fields neither Newton's or Einstein's equations would apply, and we should employ entirely different expressions. More precisely, Milgram proposed modifying not the law of universal gravitation, but another Newton legacy, the second law of motion. As you may know, this law states that the acceleration gained by an object under the influence of a force is directly proportional to a force. This proportionality is represented by a constant called mass. Now, Milgram posited that this relation actually has a more complex nature. To be precise, the part of the equation on the right-hand side should be multiplied by a function called nu, which depends on the ratio of the acceleration to a constant value, denoted as a0, which Milgram estimates to be roughly 10 to the power of minus 10 meters per second squared. The exact form of mu function is not specified by Milgram, but he claims that it should have a linear character for accelerations of the order of a0. Consequently, the second law of Newton in Milgram's theory would look like this. In simpler terms, Mond suggests that under very weak forces, the acceleration experienced due to these forces would be greater than what Newton's law predicts. Therefore, when we measure this acceleration keeping in mind Newtonian formula, we conclude that it must be caused by a greater force than is actually at play. In gravitational problems, that means that objects in weak gravitational fields would accelerate more than they should, behaving as if they were in gravitational field of greater mass. In other words, according to Milgram and his followers, there is actually no hidden mass, and the observed gravitational anomalies can be explained by merely using a different formula. If we substitute Newton's law of universal gravitation into Milgram's formula instead of the force, we arrive at these expressions. For a body moving in circle, we have also this expression relating velocity, acceleration, and the radius of the orbit. Considering this, we find that the rotation velocity of stars in galaxies should not depend on their distance from the galactic center, precisely what we have observed in reality. Unfortunately, Mond encountered one pesky problem. In Milgram's version, the law of conservation of momentum had to be violated. However, there are followers of Milgram who have modified the mathematical part of this theory. Among the offspring of Mond theories, we can mention the tensor vector scalar theory, or TVS, proposed in 204 by Jacob Bekenstein, as well as the so-called quadratic Lagrangian theory, or EQUAL. Unfortunately, to understand the essence of these ideas, we would need to delve into some specific areas of theoretical mechanics, which might not be mathematically suitable for all viewers, and we won't do it without warning. Let's just say that Professor Kyuhun Che, whose work we studied out today's material with, claims that his data align well with the predictions of the EQUAL theory. What's intriguing here is that we can try to explain the galactic gravitational anomalies we've mentioned earlier using both alternative gravity theories like Mond and dark matter, if it indeed exists. But it seems to be impossible to explain Kyuhun-Che findings using dark matter only. In reality, the average density of dark matter in the central part of our galaxy, according to calculations, is approximately 10 to the power of minus 20 grams per cubic centimeter of space, and its total mass in the solar system, for example, is less than 1% of the Moon's mass. In other words, the contribution of dark matter to the gravitational interaction of binary stars cannot be as significant as described by Kyuhun-Che. His work appears to be the first case of anomalies that can be explained only by modifying gravitational equations, which could indicate the necessity of such modifications regardless of whether we discover dark matter or not. However, things are not as rosy as proponents of Mond and related theories would hope. While these theories may explain some gravitational anomalies, they fall short in explaining others. For example, these theories produce incorrect results for the gravitational lensing. Overall, in my subjective opinion, this entire Mond story feels a lot like fitting the solution to the answer, especially considering that neither Milgram nor his followers provide a physical mechanism explaining their assumptions. On the other hand, there are other alternative gravity theories that also claim to explain observed phenomena without invoking dark matter. Among them, we can mention the so-called non-symmetric gravitational theory by John Moffat or the anisotropic geometry dynamics by Sergei Siparov. If you are interested, we can dedicate one of the upcoming videos to a brief overview of the most interesting theory of this kind. Feel free to share your thoughts on this in the comments. As for the hypothesis of dark matter, it might be too early to dismiss it altogether. After all, who knows? Perhaps one of the numerous experiments searching for it will confirm one hypothesis or another about its nature, and proponents of this concept might finally celebrate a long-awaited and well-deserved triumph. In any case, it's far too early to draw a conclusion on this matter, and there will be clearly more astonishing discoveries, original theories, and heated scientific debates ahead, everything we love about the world of science. Oh, by the way, if you enjoy this video, don't forget to hit the like button to recommend it to more users on YouTube. And until we meet again, take care.